pair that is utilizing non-click samples via semi-supervised learning for conversion rate prediction.
Hello, ladies and gentlemen. I'm here to present this paper on CVR prediction. And this work was done when I was an intern at Tencent. And first, look at the background and the challenges. Since we know the typical user behaviors involving exposure, click to conversion sequences in CVR prediction. So the CVR prediction task itself is counterfactual, which leads to the several problems. The first is sample selection bias. Because in conventional CVR models, the model is trained in click space. But during the inference time, it is inferenced on the entire space. So there are totally gaps in these two spaces, and we call it sample selection bias. And the second is data sparsity, because compared to the entire space, the samples of the click space is far more sparse, like maybe 2% or 0.2%. And the third problem is we call it the false negative sample. Because imagine this. Do we really think the absence of clicks really necessarily imply a dislike for these items? I think the answer is negative, because the absence of clicks could be attributed to factors such as exposure or position bias, when users may not be aware of the existence of the exposed items. And certain samples still have the potential to convert if it is clicked. So this basically is the problem that we focus in this paper. And existing work from ESSM that is proposed by Ali proposed a city CVR task. And this task models from exposure to click and conversion. And existing work, I mean, basically they all employ this task and conduct multitask learning. And then some causal method like inverse propensity weighting or doubly robust method was proposed to conduct the bias. And as far as I know, the current SOTA method, DCMT, proposed to model the CVR task in counterfactual space. However, let's think about this city CVR task, because the intuition behind this task is that to propose this task, we can sample the CVR task in entire space. And this, to some extent, alleviates the sample selection bias problem and the data sparsity problem. However, all these exposed yet non-click samples are actually regarded as negative in this task, because the city CVR probability is the product of CTR task and CVR task. And all these non-negatives and all the non-click samples are assigned a city CVR label of 0. And during the optimization process, we can see for all these samples, we presume that the CTR probability and the CVR probability to be near 0, so we can get a proper optimization process. And that leads to, we think this optimization process will push the predicted CVR value towards 0. And that again, I think will deteriorate the false negative sample problem. And to showcase the idea of this city CVR task, we conduct an motivation experiments. And in the first setting, we just treat all these exposed yet non-click samples as negative. And in the second setting, we treat them as unlabeled and conduct some semi-supervised learning methods. And there is a significant offline AUC discrepancies like 0.5%. And this way, we just try to model the non-click samples. And our motivation is quite simple. We kind of divide the exposure space to be click space and non-click space. And as far as we can see, in non-click space, there are actually true negative samples that cannot convert, but we argue that there are actually false negative samples that, if it is exposed next time and the user really click on this sample, it actually has a chance to get converted. And we just try to model these non-click samples because actually the CVR label of these non-click samples are unknown. And in the related works, actually they just treat them as as negative, or they just discard these labels, these samples. So again, we argue that these samples actually has a chance to get converted, and we just try to solve this false negative sample problem. And these are just some notations, and we just show paths. And to kind of solve this problem, our idea is also quite simple. We just, during the optimization process, we kind of divide the loss into two spaces. And in click space, because we think the user actually click on this space, so the CVR label of these samples are actually accurate, and we can just compute the normal cross entropy loss, and that is loss O. And in non-click space, that is our focus. We just try to calculate again the cross entropy loss. However, we are not magicians. We just don't know if these samples are actually clicked. What are their probabilities to get really converted? So this WUI just represents the probability that a user click on the sample and the sample will actually get converted. And the RUI hat is actually the predicted probability of the CVR model. And then we just kind of directly add these two kind of losses, and we just compute the loss in entire space. But the problem is WI is actually unknown, and how can we model this loss? So we just kind of do some really intuitive and naive solution. We just treat the CVR model, the prediction of the CVR model, as the pseudo labels. And there are two possible explanations. The first is kind of like a self-distillation of the CVR model, and the second is because we are doing a binary classification task. So if the pseudo label and the model's probabilities are the same, then the cross entropy loss will deteriorate to the entropy of the predicted probability. And as we know, the entropy itself, it just kind of measures the uncertainty of a probability. So if it falls to 0 or falls to 1, that is, the CVR model is very certain that if a sample will actually convert, or it's very certain the sample will not convert, then the loss is minimized. However, if RUI hat is close to 0.5, that is, the CVR model has actually no idea whether the sample will get converted, then the loss is maximized. So we kind of add this loss in non-click space as a regularization loss and kind of do this optimization. And here we do not add some weights, because if the WIUI is predicted correctly, then ideally this CVR loss is an unbiased estimator of the idea CVR loss. And also here we present a multitask framework, and we introduce CTR task, because in further ablation studies, we find that by introducing CTR task, the CVR model will actually get a very kind of significant gain. And actually, the CVR model shares the same embedding layer with the CTR task, which maps large-scale sparse input data into low-dimensional representation vectors. And also, here is some trick when we do some training, because actually, the positive samples of CTR task is far bigger than that of CVR task. So in some batches, just statistically, the CTR loss is far bigger than the CVR loss. So we just try to add some weights to the CVR task. And as you can see in the algorithm, in every batch, we just try to add some weights to the CVR task. And to be more precise, during the forward process, we just kind of get the loss of CTR task and CVR task, and we calculate their division. And to prevent some instability during training, we just add two hyperparameters, alpha and beta. We add beta to prevent the weight to be too high, because in some batches, the CVR loss could be so small and the division is so big. And alpha actually just kind of scale these two losses. And here is the system overview. It's quite simple. It's just a multitask framework, and we have two heads, just one for CTR task and one for CVR task. And actually, the CTR task is here just to totally assist the training process of CVR task, and we do not use its predictions online. And here's some intuition about why we discard the city-CVR model, because while we argue that CTR task is directly related to CVR task, because these two tasks are really similar, and if we do multitask training, we expect these two tasks will have some gains. But CTR task is actually directly related to the content, like ad creatives, and CVR task relates more to the conversion aspects, like landing page, download, installation, and actually the quality of the ad or the quality of the item is really important. And we recognize that product with high quality and competitive pricing might not attract clicks due to some less appealing creatives, but are likely to convert if they are clicked. So we just kind of divide the widely adopted CVR task and decouple the CTR and CVR task, treating them as relatively independent. So this way we kind of mitigate the false negative sample problem by dissociating the strong correlation between CTR and CVR tasks. And here are some experimental settings. We just do experiment on three data sets, one LSCP, one quite pure, that is two benchmark data sets for CVR prediction, and the last is production data set from Tencent. And we actually use AUC, log loss, and KES metric, and conduct experiments on MLP, DPFM, and DCMV2, and we can really see a great improvement on offline AUC. And this is the production data set. And also we conduct ablation study to see if the components are effective. And the nice one, the blue one, is whether we employ multitask learning with the CTR task, and we can see that CTR task really helps a lot. And the other two is whether we use reweight mechanism and whether we utilize the non-click samples. And also we do some hyperparameter evaluations, and because we introduce two hyperparameters, alpha and beta. And the trend is when alpha or beta are small or too large, their AUC is just, we can see a deteriorate in AUC, and which is quite intuitive, because if alpha and beta are too small, then we kind of let CTR tasks dominate the learning process. And if alpha and beta are too big, then we kind of lose the advantage of introducing CTR tasks. And also, we just conduct experiments on different multitask learning architecture, like share bottom, multi-experts, and mixed experts. And to conclude, the idea was really simple, and the method is really simple. And the problem of this method is we use the prediction probabilities of a CVR model that is trained on biased and sparse samples, yet we just kind of use its predictions as pseudo-labels. And that is the biggest problem. And also, we do not conduct online experiment, and we don't know whether it will really work in real-world recommendations. But during my next internship, I actually deployed this model online, and the only difference is I just kind of introduce another teacher model and kind of utilize the privilege feature distillation work, and we can see a really significant improvement online. And that is all. Thank you.
Thank you for your presentation. So, on Slido, there is Anonymous who is a bit confused. It happens. So, his question is, how do you calculate the loss of something against itself? Isn't it always zero?
No, actually, because we are using the cross-entropy loss, and it's not like MSE loss. So if the pseudo-label and the predicted probabilities are the same, they are not just zero. They are just like a curve. They are zero at the end point, but they are maximized at the middle point. It's like a curve, so it's not actually zero.
Okay. So the second question is by Joseph. Do you do negative sampling on non-exposure and non-click samples?
Yeah, we actually do some experiments with negative sampling, and it's just kind of amazing to find that if we do negative sampling to some extent, the AUC will increase. And it's kind of an intriguing question and needs further exploration.
Sorry?
We actually did some experiments on negative sample.
Okay.
Yeah.
Okay, thank you again. So we can move to the last presentation of this session.
Okay, thank you again.